In algorithmic game theory, a succinct game or a succinctly representable game is a game which may be represented in a size much smaller than its normal form representation, without placing constraints on player utilities. Describing a game of players, each facing strategies, requires listing utility values. Even trivial algorithms are capable of finding a Nash equilibrium in a time polynomial in the length of such a large input. A succinct game is of polynomial type if in a game represented by a string of length n the number of players, as well as the number of strategies of each player, is bounded by a polynomial in n. Types of succinct games. Graphical games. Graphical games are games in which the utilities of each player depends on the actions of very few other players. If is the greatest number of players by whose actions any single player is affected, the number of utility values needed to describe the game is, which for a small is a considerable improvement. It has been shown that any normal form game is reducible to a graphical game with all degrees bounded by 3 and with 2 strategies for each player. Unlike normal form games, the problem of finding a pure Nash equilibrium in graphical games is NP-complete. The problem of finding a Nash equilibrium in a graphical game is PPAD-complete. Finding a correlated equilibrium of a graphical game can be done in polynomial time, and for a graph with a bounded tree width. This is also true for finding an optimal correlated equilibrium. Sparse games. Sparse games are those where most of the utilities are zero. Graphical games may be seen as a special case of sparse games. For a two-player game, a sparse game may be defined as a game in which each row and column of the two payoff matrices has at most a constant number of non-zero entries. It has been shown that finding a Nash equilibrium in such a sparse game is PPAD hard, and that there does not exist a fully polynomial time approximation scheme unless PPAD is in P. Symmetric games. In symmetric games all players are identical, so in evaluating the utility of a combination of strategies, all that matters is how many of the players play each of the strategies. Thus, describing such a game requires giving only utility values. In a symmetric game with two strategies there always exists a pure Nash equilibrium, although a symmetric pure Nash equilibrium may not exist. The problem of finding a pure Nash equilibrium in a symmetric game with a constant number of actions is in AC0. However, when the number of actions grows with the number of players, the problem is NP-complete. In any symmetric game there exists a symmetric equilibrium. Given a symmetric game of n players facing k strategies, a symmetric equilibrium may be found in polynomial time if k equals. Finding a correlated equilibrium in symmetric games may be done in polynomial time. Anonymous games. In anonymous games, players have different utilities but do not distinguish between other players. In such a game a player's utility again depends on how many of his peers choose which strategy, and his own, so utility values are required. If the number of actions grows with the number of players, finding a pure Nash equilibrium in an anonymous game is NP hard. An optimal correlated equilibrium of an anonymous game may be found in polynomial time. When the number of strategies is 2, there is a known PTAS for finding an epsilon approximate Nash equilibrium. Polymatrix games. In a polymatrix game, there is a utility matrix for every pair of players, denoting a component of player i's utility. Player i's final utility is the sum of all such components. The number of utilities values required to represent such a game is. Polymatrix games always have at least one mixed Nash equilibrium. The problem of finding a Nash equilibrium in a polymatrix game is PPAD-complete. Finding a correlated equilibrium of a polymatrix game can be done in polynomial time. Circuit games. The most flexible way of representing a succinct game is by representing each player by a polynomial time-bounded Turing machine, which takes as its input the actions of all players and outputs the player's utility. Such a Turing machine is equivalent to a Boolean circuit, and it is this representation, known as circuit games, that we will consider. Computing the value of a two-player zero-sum circuit game is an EXP-complete problem, and approximating the value of such a game up to a multiplicative factor is known to be NP-SPACE. Determining whether a pure Nash equilibrium exists is a complete problem. Other representations. Many other types of succinct game exist. Examples include congestion games, network congestion games, scheduling games, local effect games, facility location games, action graph games, hypergraphical games and more. Summary of complexities of finding equilibria. Below is a table of some known complexity results for finding certain classes of equilibria in several game representations. Ni stands for Nash equilibrium, and C for correlated equilibrium. N is the number of players and S is the number of strategies each player faces. In graphical games, D is the maximum in degree of the game graph. For references, see main article text.